Welcome back to our Possum regression series. So far, we have explored our data, fitted a regression line, interpreted the results, and visualized the regression line. But before we trust this model, we need to validate it by checking the assumptions of linear regression. In this video, we will review a complete diagnostic process to assess whether our model meets the core assumptions. These core assumptions are linearity, homoscedasticity, normality of residuals, and the presence of influential points. Let's begin with one of the most important plots, the residuals versus fitted plots. This helps us check two assumptions, linearity and homoscedasticity, which means constant variance of residuals. We plot the predicted values against the residuals to assess how the residuals behave across the range of predictions. This is called a residual versus fitted plot. What we want to see here is a random cloud of points scattered around the horizontal red line at 0. That would suggest our model is appropriate, it captures the main trend, and the residuals or errors don't show any systematic pattern. However, if you see a curve like a smile or frown shape, it suggests the model is misspecified. That usually means the relationship between the predictor and the response is not purely linear. You might need a transformation or a more complex model. If you see a funnel shape residuals spreading out as fitted values increase, that's a sign of heteroscedasticity or non constant variance. This violates one of the key assumptions of linear regression and affects the reliability of standard errors, p-values, and confidence intervals. In our case, the residuals versus fitted plot shows a fairly random scatter of points centered around the red zero line. There is no clear curvature or systematic pattern, which suggests that our linear model is appropriate for capturing the relationship between total length and head length in possums. Next up is the QQ plot, short for quantile-quantile plot. This diagnostic helps us assess whether the residuals are normally distributed, which is a key assumption behind p-values, t-tests, and confidence intervals in linear regression. The function QQ-norm plots the sample quantiles of the residuals against the theoretical quantiles of a normal distribution. Then QQ-line function adds a reference line that represents what we would expect if the residuals were perfectly normal. If your residuals are approximately normal, the points should fall roughly along the red line. Some scatter is expected, especially near the tails, but the overall alignment should be clear. On the other hand, if the points deviate systematically from the line, say they form an S shape, bow inward, or flare outward, that suggests non normality. This may not affect predictions much, but it can distort your hypothesis tests and make confidence intervals unreliable. In our case, the QQ plot shows that most residuals closely follow the red line with only minor deviations at the extremes. This indicates that our residuals are approximately normally distributed. There is no strong evidence of skewness or heavy tails, so we can reasonably trust the statistical inference from our regression model, like the p values and confidence intervals. So far, our model is doing well. It satisfies both linearity, constant variance, and now normality of residuals. That's exactly what we want to see in a reliable linear model. Another way to check the normality of residuals, especially useful for visual learners, is by plotting a histogram of residuals. In this code, we are dividing the residuals into 10 bins using breaks equal to 10. The bars are filled with sky blue and we remove the border for a cleaner, more polished look. What are we looking for? Ideally, the histogram should be bell-shaped and centered around 0. This supports the assumption that the residuals follow a normal distribution. The shape doesn't need to be perfect, but we are watching out for skewness, which means a lopsided shape, heavy tails, which means outliers far from center, or bimodality. It means two peaks instead of one. In our case, the histogram of residuals appear roughly symmetric and centered around 0. There is a single peak near 0 and no obvious skew or secondary modes. This visual check supports what we saw in the QQ plot, that our residuals are approximately normally distributed. So far, the model for predicting possum head length using total length is looking solid. It's linear, homoscedastic, and has well-behaved residuals. Finally, let's check our influential observation using Cook's distance. These are data points that, if removed, would significantly change the fitted regression model either by shifting the slope, the intercept, or both. Cook.distance function calculates the influence score for each observation. The type equal to h in plot function draws vertical lines to represent the magnitude of each point's influence like spikes on a radar. The horizontal red line is a reference threshold commonly set at 4 by n, where n is the number of observations in the model. Any spike that goes above the red line should raise a red flag. In the output, each spike represents a data point. If a few of those spikes tower above the red line, they could be outliers. In our case, the Cook's distance plot for Possum model shows that most observations fall well below the threshold. This suggests that no single data point is unduly influencing the regression results. Cook's distance is a critical tool in our regression toolkit. It doesn't test assumptions directly, but it protects your model from distortion by identifying data points that might dominate the results. So far, our model passes every major diagnostic. It's linear, homoscedastic, residuals are roughly normal, and no points are overly influential. This gives us confidence in the reliability and interpretability of our findings. In our next video, we will take the analysis a step further by introducing categorical variables into the regression model. Thank you for watching and see you in the next video.